I suggest you start watching video for lecture 2. Posted the link. Suggest you watch till the 1:16:47, which is a little like maybe a few minutes past when they break for pizza, because he also covers questions asked during the break regarding the first part of the lecture, and we'll start discussing at 9 a.m. Pacific and about 55 minutes from now. Also, remember that we are breaking the lecture into 2 parts, so we'll only be covering in the discussions kind of like up till the 1:16:50 seconds mark. And we'll cover the rest of it in the next session next week. Okay, everyone, time to start the discussions. Hope you're able to watch the video, and after about a couple of rounds of this approach, I'd like to take a few minutes to see, after about 2 lectures this way, whether we should focus more time on the discussion. But today, let's start the discussions. What I'd like to do is probably just use the slides, and I'll start sharing them to just kind of move the discussion along and kind of explain, at least as I see it, the key points that he hits in the lecture. Feel free to stop, ask questions, and or correct me. I'm as much a learner as all of you are, not an expert on the subject. So with that, let's, and again, I'm not going to take you through the details of each of the slides, but just kind of hit the key point. Let me know whether you can see the slides on the screen. Yes?
Yep, can see the slides.
Okay, thanks. Okay, so I think, the key thing is he's kind of giving some of the motivation. We already know that, so I'm skipping that. He starts with very basic, let's just use histograms, which are just counts as a model in order to model the underlying distribution. Gets into then the discussion of why the histograms are limited or what kinds of limitations they have, especially the fact that this is in a single dimension, and when you go to even the simple data sets such as MNIST, which if you assume binary, just black and white pixels, then if each of the pixel positions of a 28 by 28 image is just black or white, 0 or 1, even that has 784 values. Therefore, when you try to kind of find the model the underlying distribution, you very quickly run into problems. And while there is a method for sampling from the distribution and inferring using a histogram, the histogram don't serve the purpose of being able to generalize in the face of large dimensions. And it kind of gives the example of typically the MNIST data is 60,000, so you have something in the order of, let's say, 10 to the 4 or 10 to the 5 turning examples. But what you're trying to do is predict the values of 202 to the 784th power, which is 10 to the 236 probabilities to estimate. So trying to do that with 10 to the 4 or 10 to the 5th basically will result in most of your models saying probability is 0, and therefore there's very poor generalization. Again, he's using this as just as a stepping stone to lead to, therefore we try to parameterize the models, which means make them smoother, make them have parameters which we can vary in order to be able to do predictions that also allows us to do generalization and use some mathematical techniques to find better the underlying distribution, get into the realm of optimization, likelihood, and so on and so forth, which helps us to get to a better ability to model the underlying distribution based on the samples of data that we have in our hand. So that's kind of the initial setup. And then it leads us to the autoregressive. And the autoregressive has 2 parts, auto and regressive. The auto is because you're generating the output from the input without labels, which is what you would typically use in supervised learning. And in this case, you do not have that, just use the inputs. And the regressive is because, especially in inference, as we'll see as we get into the details, you use each input to feed into the next stage and thereby get the output, making it either regressive and or recurrent if you use RNNs, for example. And the other things is that he touches on is, you use the neural networks to make sure that you meet certain objectives, which he talks about very early on, which is, computational efficiency, which is just being able to do it in any reasonable amount of time. Also talks about statistical efficiency, which he defines slightly, although during the lecture he tends to conflate the two, at least in my opinion, which is the ability to predict based on few samples, not a huge number of, or at least reasonable amount of data to make predictions on. And then another term that he touches on, which was new at least to me, is the expressiveness of the network, which in a sense is the ability of the network to model any data, image, or text. Thereby, and I think in this series of lectures that will become more important, how expressive the network is, that is, how good it is in modeling the entirety of the underlying data distribution versus not. And this becomes important, I think, especially in the view of GANs and generative networks, and then the ability of networks to generalize. So it's computational statistical efficiency, expressiveness, generalization. These are the things that we desire from some of the networks and architectures that we generate. The underlying distribution, once we get into the realm of probability, is the fact that any model, if it's based on probability, then must obey the laws of probability, which means that for parametric models, for all theta, the probabilities of p theta of x, where x is your input, should be greater than or equal to 0 and less than or equal to 1. And the sum of all the probabilities that for the parameters should be equal to 1. So those are the basic rules of probability that things should, that any probability distribution must obey. So that's kind of leads us into the likelihood-based modeling of distributions and fitting based on the data, determining the distribution that fits or that best gives us a model that's able to generalize and thereby generate. In some sense, he also touches on two things. Some of our models, as we go forward, we desire two things from our models. One is generate outputs which are representative or which cover the distribution of the underlying data. And secondly, if we provide an input, we want to be able to say what's the probability that that input belongs to the underlying distribution. And he also touches on the fact that some architectures are able to do one thing better than the other. For example, the made model, as we'll see, is or auto encoders are easily generating, they're capable of generating samples, but they're not inherently capable of providing probability. By that, he means that if you give it an input, it will obviously try to, it's an autoencoder, and therefore it tries to convert the input or generate an output which is the same as the input. Therefore, it's able to generate the probability distribution of the underlying data, but it, without modification, is unable to say whether, given an input, what's the probability that that input belongs to the underlying data distribution, as we'll see when we get to the discussion details of that part. So those two capabilities, saying whether an input is part, what's the probability of, given an input, that it belongs to the underlying data distribution, and then being able to generate data that is representative of the underlying data distribution. So those are the two capabilities that we seek from some of the architectures that we look at. And he says that there are trade-offs between the two. Sometimes the networks we come up with are able to do one and not inherently able to do the other. And that's something to keep in mind as we go through the rest of the lectures. I assume that given, if you've gone through any kind of deep learning courses, that optimizing and going through the maximum likelihood and understanding that by modeling the data using maximum likelihood concepts, we are trying to match the underlying distribution and reducing or minimizing the tail divergence, thereby using the methods of stochastic gradient descent then allows us to get work efficiently with large data sets and is also compatible with the neural network architectures. And that kind of setup of starting with the histogram, moving on to neural networks, which allow us to use some mathematical techniques, which then help us to deal with large data sets and with getting us to be able to generalize better and fit within the rules of probability is where eventually we are headed in this and subsequent lectures. And then how do we design? So this is the interesting part. We need to make sure that any network we design, if we stick with the realm of probability, and again, I use that term because the other way to think about this network is from an energy modeling perspective. And I think for those of you who have not been part of the deep learning, PyTorch-based deep learning network course offered by NYU, I'd suggest looking at some of the lectures because it covers the energy concepts that are related. And you'll see in this lecture also he uses that to explain certain things which are easier explained using the energy model as opposed to a probabilistic model. Although both, I believe at least, use very similar underlying mathematics. I'm not an expert on BaseNet and so on, but I think the concept that he tries to explain in the next few slides is more the fact that one of the ways that you can get the autoregressive models is to eliminate certain dependencies or conditions that if from saying every output depends on every other input. And that simplification can be done in the BaseNet kind of realm by making the net sparse. And in the case of neural networks, there are again a couple of different ways that you can achieve the same goal. And the reason you want to achieve the goal is, again, keep in mind that you want computational and statistical efficiency while having expressiveness and generalization and so on and so forth. Right. So he starts with a very simple two level network. This slide, for example, is just saying that one way to have a network that a BaseNet structure, which is basically in order for you to be able to predict xi, then all of the, it's conditioned on all of the parents of xi, which can be expressed mathematically as xi is conditioned on everything from 1 until I minus 1. That is, your next pixel is dependent on every other pixel. And as I think Shiran pointed to the blog, which also talks about, in economics and other things, basically, this is the autoregressive thing where your output is dependent on previous input. And, round and round the loop you go. That's kind of the regressive part. Each output is dependent on every output that went before you, or every input that is before you. And sorry, go ahead, questions?
Yeah, I observe one difference. Like in the blog, it says that like as you mentioned, like the input is again fed back to predict the next pixel in the loop. But that happens only at the time of inference. In the training, since we know what is the next pixel, we take that current input. We take that the true value instead
Yeah,
of the
that's
predicted value.
correct. Yeah, in the training, that's yes, you're right. And he gets into a specific example as we go into made of how that works, and that's one of the shortcomings it's of the autoregressive models is the output depends on the input in that sense, not during training, but during inference. So we'll see that that causes these networks to be relatively slow, right? Because every output, in order to generate X15, you have to first generate at X0, then X1, X2, X3, and wait for the, at least when you're doing inference, take the output sample, go back, feed it to the next level. And we'll get to that, that he explains how that happens towards the end of this lecture for just the made network. The so he starts with simple example of two inputs, and kind of this is, you know, again, the engineer haven't spent too much time on probability, but this forced me to go back to the couple of courses. I'll post links if you're interested. And you know, there are at least one or two free courses on probability which are really excellent. And basically, these are total probability rules. I think there are a few people on the call that are much more expert. They can talk to it, but it's kind of seems to provide the total probability calculation. So Px1, X2 is, you know, Px1 unconditioned, and then Px2 as a condition of X1, and then obviously you can go down the chain. And this Px2 given X1 is just an MLP or a multi-layer perceptron. And you can make sure that this guy is again probability distribution by using a softmax, because that would normalize the output with respect to this variable, ensuring that the probability rules are followed. The value of output is 0 and between 0 and 1, and the total outputs sum to 1. So the question is, then he says that one way that this is better than just doing a table-based approach in BaseNet and stuff is, instead of having it be, let's say, if it is two valued of black and white, for example, then it will be order of 2 exponent of D, whereas in our case, it's a linear function of D. And we'll understand that even better by looking at, for example, recurrent neural networks. So one of the ways that we can get better at this is to share some of the parameters as we generate the conditional distributions. What does sharing parameter, and before we get into what does sharing parameters mean, we can kind of look at them using two different examples. The first example, which he won't focus on too much, but he does briefly mention it, is the recurrent neural networks, and which I'm sure many of you are very familiar with, especially with NLP and so on, but it kind of shows how it can be used in the domain of images. And then the more relevant to our discussion, the rest of the lecture would be how we can share parameters and or make the networks more efficient by using masking, or construct the architecture of the network using masking. So autoregressive models using RNN. So remember that in our goal is, or one of the things that we're trying to model is, the output is dependent on everything that came before it. And one way that that is done, and you can read the paper character prediction using RNNs is if we have the word hello, then how we feed it to RNNs and get the prediction for the next character. What's interesting in our context of how, and this is a very good explanation also of RNNs and how sharing parameters works, is in the recurrent neural networks, one of the key concepts that is that of this hidden layer, which is fed into the next hidden layer, which is what you see here. And the fact that we use a single matrix, WHHA, W_HH, that's the same matrix that's used for each stage of this RNN. And that's the parameter sharing that happens. And the fact that there's some simplification that's done in RNNs in the following sense, that every single output down the chain, while it depends on the previous network, the way that dependency is captured is through the hidden layer values. So the fact that H determines this hidden layer, and then the hidden layer is carried on to the next hidden layer for E, allows the L prediction to happen from both H and E, and the value of H, instead of a direct path leading from L to H, it uses this set of hidden values which have come from the previous input H. And then in this case, we are using the hidden values here, which capture the E input as well as through this green path coming from left to right, the impact of H. So I think the point is that we are using the conditionality, but in an indirect way rather than having a direct path built from L to H, from this L to H and E, and from the O to H, E, and L. We kind of use this set of shared parameters and this hidden layer to have an effect similar to what we would have to generate this dependency on every previous value. So that's kind of conceptually what the RNNs help us do more computationally and statistically effectively, while retaining the ability to kind of be expressive and generate any of the outputs from our vocabulary of characters. So that's, if you will, the first example of RNNs allowing us to do what we'd like to do. However, as many of you are getting experts and know much more about this, is the fact that there's limitations. We have problems of propagation, exploding, vanishing gradients, all of that kind of stuff. But this is in the word of in the realm of NLP and characters and words. And obviously there is LSTM improvement on RNNs and so on and so forth. But he also points out that you could use RNNs to kind of within 20 epochs, and it's, at least to me, was surprisingly good, given that, as he discusses further, we provided linear input, which is everything flattened into a horizontal row, which is not how the MNIST characters are structured. As anybody is familiar with ConNet knows, obviously we are in no way with the flattening, we're not providing any of the impact of vertical dimension. It's all in a single row, but nevertheless, I think, at least to me, and I'd never tried it, within 20 epochs, you can see reasonable, although this portion here is pretty bad, but a reasonable duplication of MNIST digits. Of course, it's just 28 by 28 and binary, but still. So he then discusses, okay, what are some of the ideas that you could have come up with to improve this? An obvious one is providing coordinates and position encoding. The other idea, which we'll get to in the subsequent discussions, is to provide some kind of skip connections. That is, if you connect, for example, if a single row is just 1 to 28 pixels, given its 28 by 28 image, then providing information from your first pixel to the 29 pixels, the vertical direction, would obviously help you figure out the images much better. We'll get to that next, but the simple thing that people have done is to provide the position encoding, which then gives the XY, which appends the XY coordinates of the pixel. This is very similar, for example, in attention-based things. Also, there is position encoding that's combined in order to get, because again, in attention, you kind of lose all knowledge of the, in self-attention, for example, and general inattention, you lose all concept of position. So if you introduce positional information, such as appending XY coordinates to the pixel, then it gets, the network gets better at recognizing the pixels, and you can see that some improvement in where things were pretty bad before. Then we get to kind of the foundation of the rest of the lecture. Here, the one thing I would say, and since there was some discussion in the chat, I'll post some links to the NY course that I think Sujit and a couple of people have referred to, both because it introduces, I think, the energy-based concepts, which I think are useful and relevant in understanding some of the concepts as we go through the rest of the course. They make it easier to grasp. And also because it provides some code, if you aren't familiar with autoencoders, variational autoencoders. We'll get into a lot more of this in this course, but at least at a very basic foundational level, those lectures and the Jupyter notebooks that go with them are very handy for quickly getting up to speed on these foundational concepts of autoencoder. So the MAID, which is masking-based masked autoencoder for distribution estimation. So again, keep in mind that what we are trying to do is use an autoencoder in order to determine the underlying distribution of something that you provide to it as input. So it is an autoencoder. So obviously it generates the output, which is provided to it as its input. In that concept, it's therefore autoencoding. But now we'll see how we can modify it in order to get it to behave in the way that we want, which is, as I mentioned before, here's where it gets into the fact that while the autoencoder is set up inherently to produce samples of the underlying data distribution, so given an input, it can provide an output, and the variational autoencoder makes it easier to kind of generate different samples. But autoencoders generally can produce the samples easily, but what it can't tell you inherently until we make some modifications to it is, given an input, what's the probability that that input belongs to the underlying distribution that you are trying to model. So that's not inherently built into the autoencoder structure. And what we'll do, or what the MAID paper does, is to come up with rules by which you can modify the autoencoder so that it also produces the probability, conforms to rules of probabilities, and thereby enables you to build this masked autoencoder that enables you to model the distribution. Right? So the key thing that we are trying to set out to do is this first thing of parallelizing the computation, and eventually we'll get into, while initially we'll start with fully connected networks to keep it simple and get the concepts fully understood and baked in, and then in the rest of the lecture, in fact, in the next lecture, or the next part of the lecture that we'll cover next week, we'll also begin to bring in convolutions, self-attention, and a whole lot of those modern concepts rather than just fully connected networks. So that's what we're getting into here. This is the first example uses of a very simple, this is an fully connected autoencoder, so it just tries to produce outputs which are the same as its inputs. But the idea here is how can we modify the basic autoencoder so that it satisfies some of the rules that we want, and therefore it's able to produce probabilities and satisfy the rules of loss of probability and thereby provide us with a distribution estimation of the underlying probabilities while also being an autoencoder. So conceptually, to understand the masking, what this says is, remember that in at least this example, we have 4 inputs, and therefore, each of them says what input is. When we have a mask here, that means that that input is not connected to any of the next stage's inputs. So that's what these 4 masks to the next layer indicate. So that 3, as you can see, is not connected to any of these layers. 1, on the other hand, has connections going to all 4, so you do not see any masking for that. And again, if you look at 2, then you see that 2 is connected to this guy, therefore it's unmasked. It's masked because it doesn't have any connection to the second of the inputs. That's why you see a dark block here, and then it's connected to the other 2. So, but if you trace through this network, what you'll find is P1 doesn't depend on anything. So, or sorry, I shouldn't say P1, P of X2, the second output, which is what is obtained here, is independent of any input. Then we base the next conditional. So X3 is conditioned on X2, which is the second input. So if you trace back through this, you'll find that the connections to the output here only come from this guy. And you can trace the path back, and he does that in the lecture. You can watch the relevant section. So therefore, our probability for this guy, which is P of X3, is conditioned only on input 2. And the probability of X1 is conditioned, again, if we trace back through these arrows, is conditioned only on X2 and on X3 and not on itself, which is this guy. I'm sorry, which is that. And since it has no connections, obviously it cannot influence X1. So that's an example in a simple 3-input, 3-output autoencoder network of how masks can be set up so that we follow the rules of probability, and the condition of probability is set up in such a way that the output only depends on things that have happened previously. And we'll again look at a larger network and go through it step by step in order to understand that better. Any questions? Okay, moving on.
So, I have a quick question.
Go ahead.
On the, yes. So the mask is given as these blobs, what exactly are masks here? Are they just
masks prevent the output from being dependent? Think of it as a missing connection. So you remove the connection, thereby ensuring that, and we'll see that more effectively in the next diagram. But it essentially prevents the output from depending on that input. So think conceptually of the mask as removing a connection that exists in the fully connected network on the left and is removed on the connections on the right. So, or if you see, for example, the difference between the right network in this slide and the left one, the right network has the connections from X1 going to all 4 of the inputs. But in this case, the mask prevents or removes the connections going from X1 to any one of the layers or any one of the nodes in the hidden layer, in the first hidden layer, because all of the connections are gone. So that's what the mask does. The mask is equivalent to removing these connections. So think of it as structuring or architecting the network in a way that the mask is so the mask, what the masks are doing is they're saying which connections to remove as you construct the network. And practically what they are doing is ensuring that the dependency of the output is only on the previous inputs, thereby ensuring that this conditional stuff is met, which is to say X3 is only dependent on X2. It doesn't depend on X1. X2 depends on nothing. It's kind of the marginal probability. And then here X1 is only dependent on X2 and X3 and is not dependent on X1 at all. So the connections are removed in each layer of the network to ensure that this structure or this outputs and this conditional probability that we have set up is met.
Okay, thank you.
Any other questions? Okay, I think, to kind of get an idea of I'm going to stop sharing the slides and kind of look at the relevant portion of the video, since the next slide is basically empty since he does that. Give me a minute. Okay, let me know when you can see it.
We can see it.
Yeah?
Yeah, looks good.
Okay, so now we've seen a very simple example of this 3 output, 3 input network. He's just generalizing it to a fully connected network. Let's say that there are 6 inputs and 6 outputs. And what we are trying to do is again set up the, basically we are trying to set up a chain rule of probability calculations, which ensures that our auto-encoding network, remember that the base structure of a network is auto-encoding, which means given an input, we wanted to generate the in its output the same values as the input. Additionally, what we wanted to do, or what the made paper tried to do, is to ensure that the outputs are also probabilities, right? And one way to do that is to ensure that these conditionals are set up, which in turn means that we need to ensure that the architecture is such that the rules of probability are followed, which makes sense. And he also explains that a little bit more, which we'll get to in a few minutes. But let's say, for example, that we choose X1 in this case to be independent or a marginal distribution. So it's just X1 just depends on the probability of X1. So in which case, it doesn't depend on anything that is coming in from the input. So we do not connect X1 to the next layer. Here he uses 3 hidden layers. This is the output layer and this is the input. And so you can see that the horizontal connection from X1 to this input is missing. And however, there are connections going from this input on to the output here to generate the X1. Now, X2 can depend on anything that has gone before. And if in our order currently that we have set up, assume that, X1 obviously is coming before X2. Therefore, X2 can depend or can be conditioned on X1. The probability of X2 given X1. So X1 can feed into the network, but nothing after it, like 2 itself or 3, 4, 5, 6 cannot feed in, which would typically have happened if it were a normal fully connected autoencoder. So you eliminate the horizontal connection and the upward connection of any of the remaining X3, X4, X5, X6. So all those are gone, but then moving forward, the rest of it is the same. You can connect horizontally and you can connect down into the future. So that's what you set up as to get you this conditional distribution for X2 given X1. So X3 can now depend, again, not on itself, and not on anything in the future, but just, or anything down yet to come, but anything that came before it, you can. So that's the connection, no horizontal connection here. X1 and X2 on the other hand can feed and on and on and on. So that's kind of structure that you can set up. And you can see once you have kind of drawn this picture yourself, you can kind of understand that this is, each layer here is very similar. So you can kind of think of this as type B, if you want to classify type into, basically the structure is one of 2 types of network. One is this type B structure, which has all of the horizontal and all going down. And then there's a type A where all the horizontal connections are missing. So that's what he annotates as type A and type B, basically 2 types of network to build the whole thing. The other thing which he explains is the fact that the ordering we chose to impose here doesn't have to be that we have to start with X1 and call that P, or make the horizontal connection not happen. We could have chosen an order where we say, okay, I'm going to start with X4. So X4 is not going to be there, and probability of X4 is the marginal or unconditioned one, and then go forward through the remaining such that they are all conditioned as in this setup, and that's allowed as well, right? So, but the important thing to realize is once we choose the order, then the masks have to follow the rules to generate the conditional probabilities. So the order and the masking go together in order to generate the architecture of a masked encoder, autoencoder, which will model our distribution estimation, right? So, and the other point he makes, which will be important for the remainder of our discussion, although here we are discussing fully connected network, but the concept can be extended to convolutional networks as well as attention. So the important things to carry away from this simple discussion of fully connected network is the fact that what we want architecturally is that we don't want to, we can have a pixel prediction only based on the past and not based on ourselves or anything we see that's down the future from us. Okay, so that's the concept, and the concept is most simply illustrated using a fully connected network. Obviously, once you conceptually understand it, then it's easier to port the same ideas and take it into the convolutional space or the space of attention, where obviously the connections are much more complicated. But once you get the concepts in the fully connected network, then carrying them forward to those domains or those structures and applying it to the architecture in those structures is easier. But it's important to grasp that concept using a fully connected network. So for example, he also points out that there's no rule which says that these hidden layers have all got to be of the same size as the input. what's important is the fact that you cannot, in a conditional setup, be dependent on kind of anything in the future or anything yourself, but have to depend on the past. Right? And you can choose different order, but once you choose the order, then the mass have to kind of follow along. Right? Any questions? Because that, I think, is one of the key concepts to take away of how to architecturally modify autoencoders in order to get to them to generate probabilities and make sure that they allow us to estimate the distribution. Right? And then the paper, and he goes on to explain that, you know, you can do MADE, which is modifying the network this way to generate, again, the numbers for MNIST, about that. And he talks about, so how do you kind of figure out how good or bad these things are? And one of the ways to do that is to score the likelihood by doing an estimation or calculating something called bits per dim. And obviously, this is negative log likelihood. Therefore, the lower the number, the better the score. And so, sorry, where does he get to the bits? I'll get to this slide in a minute. Okay, before scoring, he compares just the negative log likelihood test results of different models on the binarized MNIST data set. Right, and then let's focus on the MADE, which is the network of interest we're talking about. The score is obviously less in these two hidden layers, and using 32 masks gives us the 86.64. The number of masks gives, you know, the number of various orderings that are used. As I said, each ordering goes with a different mask, and it gives us the lowest score, which is therefore the best result, if you will. And here, this is samples from a 2 hidden layer MADE network. In this case, the point he's trying to make is, how do we know that this network is actually learning and not just memorizing all of the inputs in that it's gotten in order to then be able to just spit out what it has memorized? And in order to do that, one of the ways he says that you can judge whether the model is actually learning something versus memorizing all of its inputs and spitting them out as outputs is to see whether neighboring pixels always have exactly the same value when you infer. And if they do, then you have a problem, because all it's doing is it's memorizing the input. But if the neighboring pixel is somewhat similar, but it's a distribution that's not identical to the previous pixel, then that tells you that there is some learning that's going on. And you can see that when you compare the nearest neighbor in a binarized MNIST, let's focus on the rightmost block. This 7 versus what you get here is 1. And if it was just memorizing, then it should have also output a 7. And you can see in general that while these images look similar, they are not always, see this 7, for example, if you were comparing it to this 7, it's not quite in the same orientation, and it looks similar, but it's not identical. So that tells you in effect that there's some learning going on versus it's just memorizing the input and spitting it back out as output. I thought that was kind of
Video
interesting.
is not refreshing. We can't see the 7.
Oh, sorry, my mistake. I should have shared my mistake. Apologies. Thanks for pointing that out. back. So I was pointing to this made results is, can you see the slides now again?
Yes.
Okay, so I was pointing to these scores, which are negative log likelihood scores. So, with 32 masks, 2 hidden layers gives you the lowest. And then I was talking about this made slide that he gets into. So for example, if you look at the rightmost block of pixels, and this is what I meant by saying one of the ways you can recognize is by doing a nearest neighbor analysis of the output. So if you compare the nearest neighbors, and see the prediction, what he points out is you can see this 7 is more like a 1 in this case, whereas and this 7 doesn't, while it looks similar, it's not exactly identical. So that says that the network is actually learning to generalize rather than just spitting output as input and memorizing it, if you will.
How do you get the nearest neighbor though?
You can, ultimately you're providing the input, so you know what your nearest neighbor is, right?
Don't you just start
These
from?
are auto-regressive ones.
Okay, but so
Right.
you give the same input and then look at the output.
Yeah, these are auto-regressive. These are auto-encoders, right? So the goal, as you can see, is the output will be the input, but so that is the intent of the way the network is set up. But if you want it to learn so that it's generating the value rather than just memorizing quote unquote and spitting the same value out, then one of the ways he points out that you can determine that is by taking the, he talks about that a little bit in the lecture of if you look at the neighboring pixel to your current pixel, and if the neighboring pixel is always the value that you see in the input, then you have a problem. If the neighboring pixel is a distribution around the value that you provide in the input, then the network is actually learning something. Then it's generalizing and generating rather than just spitting out whatever you gave it as input. Although the goal of autoencoder is that.
So it's not nearest neighbor in terms of the image, the whole image. It's inside the image, you mean?
Yes. Yeah, it's not nearest neighbor as in between two images. It's nearest neighbor of pixels within each image. That's what he's talking about. Nearest neighbor. Yeah. So you can see that these numbers, while they're identical to, when I say identical, I mean if 8 is an 8, but this 8 and this 8 don't look exactly the same. And then in this case, there is actually, this is a 7 and here is a 1. Okay, moving along since only 7 minutes. So, you can, much like we provided the XY coordinates, you can kind of provide various permutations, ordering, and then see which one gives you the better. The raster scan order, where you provide the inputs to the network going from left to right, and then from top to bottom. So you go from this pixel to the first row end, and then you start at the second row and then go through the second row, third row, and so on and so forth. That gives the best results. If you go column by column, this is the result. If you go top to middle, bottom to middle, blah, blah, then you get that. And then this is the one which is interesting is we talked about ordering and mask going together. And he says that for the made network and in their paper for the network that they used, you get the lowest test error when you use somewhere in the range, I think he says 6 to 7 orderings combined together. And as you go further and increase the number of orderings, then it tends to get worse. And his explanation for that is that the fact that, you don't, the expressiveness of the network begins to go down. And one of the suggestions he has, which might be an interesting thing if you're inclined to play with the code and so on, is from the made paper, is that if you use a different network or a larger network than what they used in made, then the anticipation is that this lowest point on the result will shift right. That is, the number of orderings that you can combine to get the best results, and keep in mind that every ordering has its own set of mass, will then give you a better test error. This curve in general, the shape of the curve will shift to the right. Right, and obviously one way we saw to score the made model is a negative log of P. Let's see, does he talk about it before we get into WaveNet and stuff? We'll cover in the next lecture, but he doesn't have a slide for it, but he talks about it in the lecture that one of the ways that you evaluate it is by using nats per dim or bits per dim. And the reason to do or use those two metrics to judge these kind of networks is because you want to normalize for the dimensions and not penalize the network or be invariant to dimensions that you use. So dimensions, basically, if you have an image which is RGB, then you have 3 dimensions in your image. So if you have 100 pixels, first you divide by the number of pixels, and then you divide the score by also the dimensions. So if, for example, you have a color image, then you divide by 3. If it's just a binary black-white image, it is just what it is. The other aspect is whether you take a binary log or log base 10. If you take a binary log, which is log to the base 2, then it's bits per dim. And if you take a log to the base 10, then it's referred to as nats per dim. So it's like how effectively you're able to encode, if you will. So those are the two different, you express the score, these scores as bits per dim or nats per dim. And that depends on whether you use log to the base 10 for nats and log to the base 2 for nets. Right, so that's the metric. Now, the other interesting part that he mentions and he touches on, which is where the energy concepts come into play, is why do you norm the output, or why do we output things that are normed? And there's obviously people, I welcome comments from anyone who is more expert in probability than I am, but the energy-based analogy that he refers to is, let's consider energy-based models. And obviously, the fundamental link between probability and energy to keep in mind is probability, think of it as proportional to e to the negative of energy. So if you have low energy, then you have high probability. So suppose we want the network to output high probability for the relevant pixels, and which means low energy. But so we want to drive the energy down, but when you're providing a bunch of training data, right? So the goal of the network is to drive the energy down. But what could happen, and this is easier understood in an energy concept, is the network can just provide every output to be of low energy. But that's not very useful. While it achieves a high score, it will completely fail to generalize or be expressive. And that's where the idea that we are after is it needs to provide high energy for unlikely pixels and low energy for likely pixels in the distribution. So you want that difference between a pixel which is in your distribution to be having low energy and a pixel unlikely to be in your distribution to have high energy. And that difference in energy conceptually is what, when translated to the probability domain, the normalization helps to achieve. At least that's the explanation that he provides. If there's any better explanation that anybody on the call has, I'd welcome further explanation on this topic. But at least that's the one that he provides in the lecture. Any comments on that? And that's where kind of listening to the NY lectures on energy-based modeling and how autoencoders work or understood in that concept helps as well, and is kind of in parallel to this probabilistic approach. Right? The three other things that he touches on towards the very end of the lecture right after is, so what do we aim to achieve by this, or what is the made paper trying to achieve with the network? It's trying to achieve essentially, says three things: ensure that the probability distribution sums to 1, and then structure the network in such a way that the conditional probabilities, when multiplied together, they satisfy the chain rule. And this then ensures again that we are adhering to the laws of probability and are normalizing things in such a way that the network achieves the goal of giving low probability to undesired values and high probability to likely values that we are expecting to see in the underlying distribution. And then he talks about how do we train. We train it by providing it input and then summing it over each of the data points. And then how do we sample? And this is where the thing that Sridham talked about even in the blog is the sampling is the interesting part. You give it an input, you take, for example, let's say that X1 is the unconditional output that we choose, then we provide the output to be the first output to be unconditional. We just sample, take that output, provide it as input. So we are feeding or connecting the output to the next input X2, and then again run the network forward, generate X1 and X2, take both of those from the output, shift it to the input, and you can see that this is going to be a fairly slow process, and that's one of the drawbacks or the disadvantages. And he talks about, the made paper taking them about 10 minutes to generate one MNIST example digit. And obviously for megapixels, this would be fairly